The final session of the day, we have Nicholas Earl, who's going to talk to us about AT2020nov. And over to you. I will give you a 5-minute warning.
Sounds good.
Wave at you.
All right, thanks. As introduced, I'm Nicholas Earl. I first want to say thanks to the conference organizers. It's been great, excellent experience so far. I want to talk today a little bit more on a science-y topic, right? AT2020nov is a relatively recently identified TDE that we've been following up with EZ and ZTF photometry. And the background here is not this TDE, unfortunately, but it is a simulation of a TDE. You can show how cool they are. So the motivation for why we are studying TDEs and why we really want high cadence, really deep photometry and good spectroscopic follow-up with TDEs is really the fact that we need to explore or desire to explore this intermediate mass realm of the black hole mass population, right? To do this, though, requires that we understand the physics of tidal disruption events, which, as it stands right now, aren't fully understood. There are accretion mechanisms and underlying physics which we don't fully understand. So studying them in detail is going to help us kind of reach that point. And this is, a corollary to this is understanding its relation to its black hole and the black hole properties, as well as the host galaxies, the host galaxy in which it finds itself, right? And it's also very important that we start to develop some kind of strong foundational understanding of tidal disruption events and the emission we expect from them in preparation for LSST, where we think that the number of TDE candidates is going to increase by orders of magnitude. Just sort of an anatomical representation of a tidal disruption event, right? They occur around black holes that are less than roughly 10 to the 8 solar masses. Otherwise, your tidal disruption radius is inside your event horizon and you get swallowed whole. Star hits tidal disruption radius, gets spread out into a debris stream. That debris stream coalesces into an accretion disk, and this accretion disk releases emission, generally in the X-ray, and then later reprocessed to UV optical, and that's what we see in our telescopes. These are, of course, relatively rare events. Hopefully we want to increase that both with EZ and LSST in the coming years. Just some historical context, right? So way back in the 70s, we had the first implication that supermassive black holes could disrupt stars. It wasn't until the 80s that we started getting some theoretical foundation for how this happens, right? What happens to debris, how the emission behaves, follows this, negative 5/3 power law decline. Emission primarily happens in the UV and X-ray. Fast forward to the 2000s, mid-2010s, we get estimates on the rates we expect to see. We get neat applications of the loss cone theory. Fast forward a couple more years, and we start getting some really nice unified TDE models based on realistic simulations, things that start to help us understand how the super Eddington accretion happens and what the emission physics look like, and some indication of how geometry affects what we see, both photometrically and spectroscopically. In the background here is just a plot of publications related to tidal disruption events, and you can kind of see that within the last half dozen years, we've really kind of started to explode. So it seems to be becoming more and more of a popular thing as more and more candidates are detected, and we expect it to continue. So there are two sort of conceptual models that describe sort of the behavior of a TDE and how we think the emission, how we think we can understand the emission. The plot on the left kind of shows the traditional model where tidal disruption event happens, the material that's left coalesces into accretion disk. You get polar outflows or jets. You get X-ray radiation. You get this reprocessing layer. And depending on your orientation, you can see variations of X-ray, X-ray only TDEs, a mixture of X-ray and UV optical TDEs, UV optical only, radio emission, various varieties of TDEs. On the right plots, is sort of a different idea where the tidal disruption event occurs, the star gets spread out into some debris, and the debris actually collides with itself. It doesn't immediately form an accretion disk, and it's this sort of shock produced by this self-collision that produces the flare that we see. There are, many differences between this and the original model. Chief among them, we don't expect to see a lot of X-ray emission from, these types of TDEs. But whether or not we see X-ray emission in general has a lot to do with the amount of material that's in the supernuclear environment of the black hole and the orientation at which you're viewing it. So trying to disambiguate between these two models is still an ongoing process. So here I'm just going to introduce AT2020nov. It was first identified back in 2020 by ZTF with a, back in 2020 with a ZTF G-band magnitude about 19.67. It was announced in alerts, and we started follow-up with EASY. It showed strong helium-2 and nitrogen-3 emission, one of the initial spectra that was taken of it, which could be suggested of Bowen fluorescence mechanism. And the WISE color of the host was not clearly AGN-like, so that kind of substantiated the notion that it may be a tidal disruption event. The plot I show here is just the ZTF and the EASY data and the location of the sort of complementary spectroscopy that we have coincident with this event. So the first thing that we end up doing is fitting the light curves, right? Here we use MOSFIT, which is a fitting routine that can do several different types of transient events, among them TDEs, but supernovae and many others. It's great because it deals with each band individually. So obviously, the more data you have, the more observations in each band you have, the better the fits will turn out to be. What's great about ZTF and EASY is that we have really great coverage of both the rise and the peak in this case, which is really necessary for constraining the estimates on the black hole mass. In the table, you can kind of see a bunch of parameters. I'm just going to point out a couple of them, right? So in this case, we see that for AT2020nov, we expect a supermassive black hole mass of about 7.2. In this case, the estimated stellar mass was about 1.38 solar masses. And all this together gives us sort of an initial disruption time about 105 days before peak flare. The next thing to do is to start characterizing the host to understand sort of the environment, where this TDE happened, and how it might be related. To do that, we take some archival data from GALEX, PanSTARRS, 2MASS, and WISE, and we do a population synthesis analysis using the prospector code, which gives us this nice host spectrum. And we use a continuity star formation history from Johnson et al. 2021. And in this case, by default, it uses about 3 time bins. So our star formation history plot here is not well sampled, but it's good enough to get an idea of the behavior, at least in the last 100 million years and a little bit beyond. And so it kind of demonstrates that after a period of high star formation, it goes into a quiescent age, and then recently it seems like something has rejuvenated the star formation, whether that might be minor mergers or some other mechanism we haven't yet fully investigated. So in this case, we see that the host galaxy is something like 10 to the 10.8, 10 to the 10.9, and a star formation rate of something around 1.1. So now we take this and we throw it in some color magnitude diagrams to try to look at it in relation to some of the other TDEs in literature. On the left here is sort of just a specific star formation rate versus stellar mass with some other TDEs pulled from French et al. 2020 and Hammerstein et al. And the background is just sort of your selection of SDSS galaxies. We do see some indication that our guess from the prospector star formation history is pretty consistent with this. It's not quite, actively star forming in this case, a little bit on the border of transition, sort of still in the Green Valley, but otherwise broadly consistent with what we'd expect. On the right here, we have some color cuts from Salem 2014. We see here, just looking at sort of the young stellar population, that we do see a lot of young stars in the host galaxy for AT2020nov, and that this could be, as the star formation history suggests, something that's recent. We do some host morphology, do some analysis of the host morphology. The latest legacy imaging survey data release includes some great Sursic indices estimates. And so just from our stellar mass that we calculated using Prospector, we can plot that against our Sursic index, and we do find that it is roughly consistent with the literature. French et al. 2020 estimated Sursic indices for TDE hosts between 1.5 and 6. And this is expected. We do expect that most TDE hosts have high central mass concentrations, which of course incidentally increases the chance that some star would wander close enough to the central black hole to cause a tidal disruption event. So now I'm going to get more into even the more preliminary analysis, and that is looking at the set of spectroscopy that we have for this event. So we have spectroscopy from both before and after the peak. Of course, analyzing the spectroscopy is a little bit difficult because we don't have a pre-flare spectrum, which makes it difficult to disambiguate any line emission evolution from host contamination at this point. There are ways to remedy this, of course. It's been roughly 2 years since the TDE occurred, so soon-to-be follow-up spectroscopic observation would help us get some kind of like default host spectrum, which we can then not only use as the continuum and subtract out some of the attenuation. Alternatives would be to scale the Prospector host model using pan-stars or easy data, and then use that as an anomalous continuum. But this doesn't stop us from trying to do science where we can. So we sort of developed a modeling framework that lets us sort of simultaneously model all emission features at the same time in these spectra. And we, of course, disambiguated some of the narrow line features we think are from the host, which are shown in green. What's the most interesting thing to pull from this plot is the fact that the broad line emission seems to be split. So we're getting sort of double peaked Volmer broad line emission, which is pretty unique in the TDE landscape. I think the only other one that comes to mind is the 2018 HYZ that also showed double peak Volmer line emission. And we see it pretty prominently both in H alpha and H beta. And this is quite interesting. It can suggest a lot of things. One is that we may be actually viewing the accretion disk, which is pretty interesting. The asymmetry and the amount of emission in the blue shifted broadline features versus the red shifted broadline features could indicate a shock origin and could indicate also outflows that are occurring in the accretion. So from there, we can just calculate the integrated flux under these emission line features and continually contextualize our host galaxy. In this case, we do all that. We throw it into a BT diagram. Again, we see that the host galaxy is roughly consistent with other host galaxies in the literature. In this case, we do see it to be some sort of Seifert composite type. And roughly consistent across the board with the recent increase in star formation. It could have been moving over time. But in that, we don't see anything too crazy about the state of the host galaxy that would suggest anything kind of out of the ordinary. Okay, so I don't know if I ran through this really fast, but conclusions. So I guess the most important thing to take away from this is that having good cadence and combining photometry from several sources is really paramount to constraining the emission behavior of tidal disruption events. This is hopefully going to be something more prominent in the future, where LSST and LS communications with broker systems, and is really going to just facilitate broad follow-up observations in many different bands that we can really take advantage of, especially for TDEs and constraining a lot of the behavior. And of course, consistent photometric observations, especially some observations that capture the rise and the peak of the light curve, are especially useful for constraining the black hole mass estimates. So that's something that we benefit from EZ and ZTF, and with the cadence of LST, certainly want to see that continue in the future. Overall, the mass of the host of AT2020nov does show recent star formation rejuvenation, possibly from some minor merger, which of course will be some part of our further analysis of the TDE. We do find that the high Sarsic index is consistent with our expectations of TDE host galaxies. Most interesting from this object is that the spectroscopy shows this sort of rare double-peaked Balmer line emission, which could suggest outflows or a shock origin, as I mentioned. It also raises the possibility of doing a geometrical analysis to get some kind of idea of the inclination or the overall geometry relative to our observations. And of course, this is, as I stated, preliminary. Our work is ongoing with publication hopefully in a couple months, so input and discussion is always appreciated. And that's it. Thank you for your time.
Thank you for a very nice talk. Do we have questions? Yes, all over here. Thanks for the exercise, Sebastian.
The short version of my question is, do you have any UV data?
Yes, we do have UV data. We
Okay.
actually have we have many other data, but it is in such an early state that we don't want to draw huge conclusions on it. I would say wait for the paper.
Yeah.
But yes, we do.
Okay, that's exciting because it's cool to see that you see the double peak structure, same as we saw in 2018 HYC.
Yes.
And 2018 HYC also had this weird UV behavior at the late time, which we kind of linked to the double peak structure. So it would be really cool to see what this one does in the UV. So
Yes.
keep an eye out.
We are using HYZ as a primary comparison, so I'm certain we'll reach out and see if there's any like obvious things we can overlap on for drawing conclusions based on this.
Great talk, Nick. So a lot of your work really required this detailed analysis with spectroscopy, and that's something you're not going to get, of course, for the most part with LSST. How feasible is it to really do a population study of TDEs if we don't have Balmer lines? What more can we say morphologically, or what more can we say from really deep galaxy image stacks? Is that enough to sort of tell us more about the population of TDEs, or do we really have to consider a LSST follow-up spectrographic program for this?
I'm a little biased because I'm a spectroscopy guy, so I'm going to say that you always need spectroscopy. That said, as it stands now, because we don't have a really great foundation, a theoretical foundation for understanding the emission mechanisms and the physics involved in TDEs, to understand where the ionization is occurring, I do think we have to have follow-up spectroscopy. Perhaps in the future it doesn't need to be at such a high cadence with so many epochs. It might be at some point, we may need one before, one after the peak of the light curve, and then one maybe later on. But I certainly can't envision TDE population analyses without good spectroscopy, unfortunately.
And can I quickly ask a follow-up of this a second? Could you go back into your time series of spectra?
One?
What the heck is going on at 266 days with H alpha? It disappears and comes back. What?
And which one? I'm sorry.
The 266 days H alpha, it just disappears and comes back, basically.
Yeah. Yeah, there's a lot of strange things happening in these spectra.
Oh, you should probably use the mic.
What's that? Oh yeah, sorry. Yeah, so there's a lot of strange things happening in the spectra. So these two spectra are from the Wife's spectrograph. They're the only two from that spectrograph. And so we think that it could just be an issue with the spectrograph, hopefully. But you know, how astronomer of me to blame my instruments instead of myself. So we do keep it in now just to see what the behavior is, but we don't put much stock in what we get out of it. We are holding out some hope that maybe once we get a spectrum of the host galaxy, that maybe some more prominent features that are buried in there might reveal themselves. But in general, we probably will not use these two for the final spectroscopic analysis. But yeah.
But can I push on or poke at one point that you just made? That you said you don't think we can publish results without good spectroscopy. Can you define good? Like, what about crappy spectroscopy? Can you use that? I mean, obviously, you need your flux calibrations to be correct, but like, can you use R of 100 to do half of this?
Maybe, right. Certainly not, you couldn't use an R100 spectrograph to do analysis on this particular object because this complex H alpha region would be completely unresolved on an R100. So you would effectively know nothing about the double peak Balmer emission lines. However, you could, for instance, you know, if, for instance, you know, do I have a pointer? Okay, no. If you can imagine where, you know, helium-2 or N3 might be, those are generally broad sort of features that exist in spectra, certain types of spectra for certain types of TDEs, and certainly that could probably be looked at using some low-resolution spectrograph. But you know, there has been an effort to figure out just how good of a spectrograph you need to do good TDE analysis. We have been trying to push for Gemini observations, for observations with just, you know, really high spectra, high resolution spectra to see what we can find. But in general, there is a too low, and we don't know if there is like a high enough yet.
Great. We still have time for questions if anyone has one. No? Okay, great. Well, let's thank our speaker again.